Well, good morning, everybody, and thank you so much for joining us today. I'm your host, Peggy Tuck. The focus of today's webinar is process cooling towers. Maintaining cold water temperature does matter. Now, first, I'd like to tell you a little bit about our featured company. For more than 60 years, Star Cooling Towers has been designing, constructing, repairing, and upgrading towers. As an industry leader, Star is constantly developing newer methods in order to serve the growing needs in the industry, and they've built a reputation for quality, value, and superb customer service. Our presenter today is Jim Smith. He is the president of Star Cooling Towers. Jim has more than 36 years of experience in HVAC, petroleum refining, chemical process, and power generation cooling towers. Since 1988, Jim has been the president of Star Cooling Towers LP in Houston, Texas. He is an expert on the design, construction, repair, and maintenance of evaporative cooling towers. We will be taking your questions following this presentation. So if you would like to submit a question, just look on the right-hand side of your screen and you'll see a little section to submit your question. And now it is my pleasure to introduce our very special presenter today, Star Cooling Towers President, Jim Smith.
Well, thank you for that introduction. Good morning, everyone. My name is Jim Smith, and I will be your presenter this morning. The intent of this presentation is to emphasize the importance of maintaining cold water temperature in a water-cooled plant. Provide the cooling tower owner-operator a basic understanding of how a cooling tower operates and describe the various components. Discuss the vital role evaporation plays in the transfer of heat from the water. Examine the factors affecting cooling tower performance, such as wet bulb temperature and heat load. And finally, we'll review an effective inspection and preventative maintenance program that is essential in the safeguarding of the efficiency and lifespan of your cooling tower. The cooling tower is often the forgotten component of a water-cooled system in terms of maintenance attention. In many facilities, the cooling tower is located outside the unit boundaries, a lot of times in the back of the plant. And it's a good example of the phrase, out of sight, out of mind. A cooling tower is a simple device, and as such is quite reliable. But unfortunately, with this reliability sometimes comes a lack of attention. The structure can be sound, rotating equipment turning, and water falling, but if the components that contribute to the efficient exchange of heat are not properly maintained, cold water temperatures will increase. An increase in cold water temperature may or may not be a problem for the process it serves. The tower may have been oversized, or the heat load had been reduced over the years, reducing the load on the tower. But if the cooling tower is not conservatively sized, undersized, it could have a negative impact on your process. Particularly the older towers that were built prior to acceptance testing and performance guarantees were intentionally built short in the competitive environment. It was not unusual to see a cooling tower that maybe was 80% of design, but because of the conservative nature of the design conditions, it went unnoticed, but it would be on the borderline. So what factors can increase cold water temperature? Your heat load may be larger than the rated capacity of your cooling tower. Your design wet bulb temperature may be low for your area. Your fans may not be utilizing all the available horsepower. And finally, your cooling tower may have lost cooling capacity resulting from the lack of proper maintenance attention. So water cooling in the processing industry contributes significantly to the operating cost of the plant. The cooling tower sets the temperature levels of a water-cooled plant process or system, determining its production, energy utilization, and the profitability of the plant. Every cooling tower is designed to deliver a specific cold water temperature at a combination of wet bulb temperature, heat load, water flow rate, and airflow. This design cold water temperature would only be expected at the design conditions and only occur during the summer months. During the cooler months, cold water temperature would be significantly lower than design, in most cases allowing a cell or cells to be shut down for maintenance. To determine the impact of cold water temperature can be determined by asking, is there a difference in plant capacity or operating cost in the summer versus the winter? And if the answer is yes, then some temperature-sensitive processes are probably being impacted by cold water temperature. Any reduction in performance can be expressed in terms of reduced product output with revenue loss, or higher energy usage, increasing operating costs, or any other key performance indicators. A cooling tower is a heat exchanger inside of which heat is withdrawn from the hot water by the mixing of the air and water. Heat transfer occurs through a combination of latent heat exchange and through evaporation of a small portion of the water to be cooled. Hot water from the heat source returns to the tower and is distributed evenly and equally through nozzles over the top layers of fill. The heat transfer surface, which we call fill, breaks up the water. It interrupts the vertical progress, causes the water to cascade through successive offset layers of splash bars. The fan draws outside air into the fill, creating the most intimate contact between the air and the water. The fan stack houses the fan assembly, providing an eased inlet for the incoming air to the fan. Every cooling tower is equipped with a method to discharge water, which we call blowdown, which is needed for water chemistry. When the cycles of concentration are reached, you discharge a certain amount of water and replenish it with fresh water, which we call makeup. And the makeup water is there to replenish the blowdown and make up for evaporation or any drift loss from the cooling tower. The two most common fill direct cooling towers is the cross-flow induced draft, which the airflow direction is across the water flow, and the counterflow induced draft, where the airflow direction is counter to the water flow. If we first take a look at the cross-flow, you can see it's easily recognized as the louvers go up the entire face of the tower for the whole longitudinal length. In this case, this distance is approximately 30 feet from the curb up to the top of where the hot water basin is. You can also see where the return riser is coming up to that elevation. Another way to distinguish a cross-flow tower is that the end walls are sloped to conform to the airflow, because you have the higher velocities at the top and the lower velocities at the bottom. The counterflow cooling tower is quite different. As you see, the air inlet louvers are only at the bottom. The walls are square. The return risers are just 5 to 6 feet above the air inlet louvers, and that shows where instead of 30 foot of packing, we would probably have 5 to 6 feet of film fill in the counterflow cooling towers. We look at the cross-flow cooling tower. The hot water is returned through a large distribution header pipe and is discharged through a flow control valve, which is designed to throttle the water to even the levels in each independent basin. Below the valve is a splash box that incorporates baffles to take the energy out of the water, allowing the water to be still in the basin. And the basin floor is a series of gravity flow nozzles that are typically spaced 12 inches by 12 inches that distributes the water evenly and equally over the fill. On all the large cross-flow towers, there's splash fill, and it can consist of wood lath, or it could be 4-inch wide, 6-inch, or 8-inch wide formed PVC splash bars. These splash bars are evenly spaced horizontally and vertically, typically an 8-inch vertical by 8-inch horizontal, and can be installed either perpendicular to the airflow or parallel to the airflow. The air inlet louvers are designed to retain the water in the cooling tower and equalize the air into the fill area. Because of the intimate mixing of the air and water, there has to be a means of stripping out the water before it travels to the fan. So drift eliminators are installed to provide sudden changes in air for the water and the air droplets. The air droplets cannot make these turns. They impinge and film back into the wetted section of the cooling tower. Due to tremendous torsional forces of a large fan and high horsepower, unitized steel mechanical supports are needed to provide a constant plane relationship between the motor and the gear reducer. And this is true in both cross-flow and counterflow. These supports can be steel and I-beam and plate, or it can be I-beam or channel, depending on the size of the fan and the horsepower. The counterflow cooling tower is quite different. The hot water comes into an individual header in each individual cell and has a series of distribution laterals coming out either side that incorporate low pressure distribution nozzles. As you can see, the film packing is cubes of PVC, and they can be different depths determined by the cooling requirements of the cooling tower. Again, drift eliminators are installed horizontally above the header system to remove the water droplets before it goes to the fan. And again, the mechanical equipment, rotating equipment, is identical to that of the cross-flow cooling tower. Evaporation is utilized to its fullest extent in a cooling tower designed to expose the maximum transient water surface to the maximum flow of air for the longest time. This highlights an aspect of cooling tower performance that those in the industry would not typically recognize, that 70 to 90% of cooling is due to evaporation of a small amount of the water to be cooled. Obviously, by increasing the time the water is mixing with the air, the greater the cooling effect. But due to economic considerations, there is a limit to the overall height of a cooling tower. So the most economic method to increase the time the water is in contact with the air is with the installation of fill. If we were given a requirement of cooling water from 85 degrees Fahrenheit to 70 degrees Fahrenheit at a 78-degree dry bulb temperature and a 50% relative humidity. Using only sensible heat transfer as in an air-cooled heat exchanger, this would be impossible because the dry bulb temperature of 78 is higher than the desired 70-degree Fahrenheit cold water temperature. With this process of evaporation that occurs in a cooling tower makes the solution an easy one. This evaporative cooling process can be illustrated on a psychrometric chart. If we come in and we intersect the 78-degree dry bulb temperature at the bottom of the chart, and we come up to the 50% relative humidity curve, we can come over, and at this point we see that represents a 65-degree wet bulb temperature. We have the 15 degrees that we're going from 85 to 70, so our total heat content, or enthalpy, increased from 30.1 BTUs to 45.1 BTUs, which is 15 BTUs gained from the water. This change of condition of a pound of air, of dry air as it moves through the tower and contacts a pound of water, we have a liquid to gas ratio of 1 and is denoted by this solid line. A BTU is equal to the gain or loss required to change the temperature of 1 pound of water by 1 degree Fahrenheit. The temperature of 1 pound of water was reduced 15 degrees Fahrenheit. If we look to the right at the humidity ratio, and we come over and we find that we started at 72 grains of moisture and we ended at 163 grains of moisture. So this moisture content of a pound of air increased from 72 grains to 163 grains is 91 grains of moisture. 7,000 grains equals 1 pound. So an increase of 91 grains is 0.013 pounds. The latent heat of evaporation of water at 85 degrees Fahrenheit is 1,045 BTUs per pound. So 13.6 BTUs of the 15 BTUs removed from the water, 90% of that total happened from evaporation. So let's look at, when we talk about a small amount of water that's evaporated to get this cooling effect, the approximate formula is the rate of evaporation can be approximated by multiplying the total circulating water flow in GPM times the cooling range in Fahrenheit times 0.0008. So in our example, if we assume that we were circulating 10,000 gallons per minute at the 15 degree Fahrenheit range, which is the 85 to 70, times the 0.008, we see that we were losing 120 gallons per minute lost to evaporation. So we'll talk about heat load. The heat load is actually determined by the process it serves. Originally, when the tower was first designed, manufacturers of the individual process equipment provided the water flow rate and temperature requirements of each piece of equipment, the total of which would represent the design BTU per hour for the heat load. The size of the cooling tower is proportional to the heat load. If the heat load calculations are low, the cooling tower would most likely be too small. If the heat load calculations are too high, the cooling tower obviously would be oversized. If we look at the difference between the hot water temperature and the cold water temperature, we refer to this as the cooling range. The cooling range is a function of the heat load and water flow. A lot of times, the owner-operators take the range as something that the cooling tower provides, but this is no function of the cooling tower. The cooling tower will only provide the cold water temperature. The range is a function of the heat load and water flow. The approach is the difference between the cold water going out and the wet bulb temperature. And typically, average approach, it would be 5 to 6 degrees to the wet bulb. The heat load is expressed in BTUs per hour. So if we take the GPM times 8.33, which is the weight of 1 gallon of water times 60 minutes, times the cooling range, it gives us our BTUs per hour. So if the flow rate changed, you would see that the cooling range would change, either it increase or decrease, or if the BTU load itself changed, we would be seeing a different cooling range. The wet bulb temperature is the lowest temperature to which air can be cooled by the evaporation of water. That's the proper definition of a wet bulb temperature. It's important to note in our example, the same amount of enthalpy exchange or cooling effect would have taken place had the air entered the tower at 65 degrees and 100% relative humidity, which by definition is a 65-degree wet bulb temperature. The wet bulb temperature is the critical design variable and the primary basis for the thermal design of a cooling tower. On the days when the wet bulb temperature is at design, the tower will produce its stated capacity. At higher than design wet bulb temperature, the tower's capacity to produce this design cold water temperature decreases. And at lower than design wet bulb temperatures, the tower's capacity to produce cold water temperature increases. Every location has a unique design or worst case wet bulb temperature that is published by organizations such as ASHRAE and can easily be obtained. For cooling towers, typically the design frequency level is 1%. Here's an example of some published data on the wet bulb temperature. If we look at Port Arthur and we come over and we see a 1% frequency level, is at 80.8 degree wet bulb temperature. Inspection of cooling towers should be one of the most important maintenance items on the owner-operator's schedule. It's effective for minimizing failures and efficiency losses. Regular inspections coupled with proper preventative maintenance and a minor repair schedule will minimize large expenditures on your cooling tower equipment. But remember, the outcome of the inspection is directly related to the competency of the individuals performing the inspection. A good inspection starts with an on-site pre-inspection meeting, initial commencement meeting with the owner's team, where you can discuss the foundation of a good inspection. Each cooling tower is unique and has a variety of different characteristics. And in this meeting is an opportunity to understand the client's needs and the operator's concerns. Start with the cold water collection basin. The basin has two important functions. One is the collection of the water to be pumped back to the heat source, and it's the primary foundation for the cooling tower structure. A visual inspection of the masonry for cracks, leaching of calcium, and spalling of any of the masonry materials. The base anchors and anchor bolts should be inspected for corrosion and cracks or any other problems. And the structure below the water level, obviously this is a time when the basin is empty and you have an opportunity to inspect the structure that's normally submerged in the water. Also, the screens that separate the basin from the pumps should be inspected to make sure it's in serviceable condition and to identify any debris that might be in the screens that might identify problems in the tower, such as maybe fill that's coming apart or wood pieces that from deteriorated structure. Sometimes these can be very telling. We'd look at the stairways and escape ladders, any access to the tower, and the ladders and stairways should be visually examined and deemed to be safe. And any unsafe conditions should be immediately reported to the plant contact. The casing or the siding on the exterior of the cooling tower acts to contain water inside the tower, and it provides an air plenum for the fan, transmits wind loads to the framework. The air inlet louvers retain circulating water within the tower and equalizes the airflow into the fill. We would look for any holes in the casing would create air bypass or leakage of the water down the walls or spraying out onto the ground. The louvers, siding panels to make sure that they're secure, they're properly caulked, and identify any problem areas. The most commonly used materials for the framework is wood, which would be treated Douglas fir or treated redwood, and fiberglass, which would be polyester fiberglass or vinyl ester fiberglass. Common framework problem areas in wood is biological attack. And this biological attack is in two forms. It could be a surface attack where the organisms, these are microorganisms that feed on the wood. It can degrade the surface of the wood. Or the most dangerous type of wood decay is an internal attack where the organisms degrade the internal wood components. These microorganisms feed on the cellulose fibers inside the wood and turn them to pulp. And this is a dangerous type of wood decay because the surface of the wood appears to be sound, where in reality the wood inside has no structural strength. And it occurs in the areas that are warm and moist, such as the plenum area, but not in the fill areas, the water washed areas. The microorganisms aren't able to grow. Chemical attack, commonly known as delignification, attacks the surface of the wood and water washed areas. The chemical breaks down the lignin within the wood, leaving behind the cellulose fibers, which is washed away. The danger of this type of attack is that it reduces the overall size of the timbers, sometimes as much as a half to 1 inch in an older tower. And this reduction in size is proportionate to the reduction in strength and can significantly reduce the structural integrity of a wood framework. Fiberglass shapes, due to their superior decay resistance compared to wood, fiberglass is prevalent in both the construction of new towers and repairs to existing towers. But for this reason, their resistance, there's a tendency to overlook fiberglass structure during inspections, although there still can be problems within a fiberglass structure. The prevailing FR deficiency is not caused by the manufacturing process of the fiberglass or the structural design of the structural members by the OEM. It is member cracking at connection points caused by over-tightening attaching bolts. FRP members should be inspected for cracks and deformations such as hole elongation or deflection. UV damage can range from fading and chalking to more advanced instances of fiber blooming, which is exposed glass fibers. The fan deck, as part of the tower structure, acts as a diaphragm for the loads, transmitting dead and live loads to the cooling tower framework. And it also provides a platform for the fan stacks and for personnel accessing the mechanical equipment or distribution systems. Handrails should be inspected with the fan deck. Fan deck is exposed to sunlight, ice, and rain. Deterioration of the plywood and T&G fan decking is commonly found during inspection. Water distribution. In the cross-flow towers, we have elevated basins above the fill. Components of the hot water basins are designed to work together to evenly distribute water over the fill. And what we mean by that is that the splash boxes, the flow control valves, the basin curbs, and the nozzles all need to be in good working order to provide good, even and equal distribution of the water over the fill. Counterflow towers utilizes a pressurized system of closed pipes. We have a header pipe and laterals in each individual cell. The low pressure spray nozzles provides even and equal distribution over the packing. And this nozzle spray actually contributes to the overall heat transfer. So distribution. And the reason I say that 3 times is it's extremely important. No matter how much water and air is going through your tower, it will not perform satisfactorily if they are not thoroughly and evenly mixed throughout the tower. Poor water distribution can severely reduce tower performance. The importance of even and equal distribution of water cannot be overemphasized. And this is one of the least expensive maintenance items on a cooling tower. With the cross-flow tower, making sure that all the nozzles are intact, they're not plugged, missing, or damaged is extremely important. Making sure that the daisy wheel below the orifice body is in serviceable condition. Making sure that the curbs maintain watertight integrity where there's not water bypass. And the splash boxes are functioning as they should, and that the flow control valves are serviceable, allowing the balancing of the water in each individual cell. And the counterflow towers with the closed pipes, it's important to remove the nozzles and hand clean and inspect. And once removed, utilize the circulation pumps to clean and flush the header lateral system. This will really pay dividends in maintaining the efficiency of your cooling tower. Also, it's important to note that with a missing nozzle, this creates a fire hose effect into your film fill and can create holes all the way through, large holes through the fill, which is going to allow air and water to bypass. The fill is one of the single most important components of a cooling tower. Its ability to promote both the maximum contact surface and the maximum contact time between air and water determines the efficiency of the cooling tower. There's 2 basic fill configurations or classifications. Splash fill. Splash fill consists of many offset layers of wood slats or PVC bars spaced evenly both vertically and horizontally, suspended on mesh fill hangers. And these mesh hangers that the fill is suspended on can be PVC coated galvanized wire, it could be stainless steel wire, or it can be glass reinforced polyester grid hangers. and these need to be maintained in good condition to keep the fill installed firmly and evenly into the tower. Film fill is quite different than the splash fill. The film fill causes the water to spread into a thin film flowing over the large vertical areas of PVC to promote the maximum exposure to the airflow. Made using thin sheets of vacuum-formed PVC, which are assembled into packs supported on horizontal fill supports. And these film fills have the capability to provide more effective cooling capacity within the same amount of space. This is why when we talked earlier about a 30-foot fill height compared to a possibly 5-foot fill height in the counterflow tower, that is the result of the high performance of these film fills. And there's a range of clog-resistant fill designs available today with filing resistance. Driftlimators are designed to remove water droplets from the discharged air. Manufactured of 15 mil PVC sheets, vacuum formed into a 3-pass design. The 3-pass means there's 3 changes of air direction. It causes the air droplets to make sudden changes in direction. The droplets are deposited back into the tower. The things on an inspection you look for is that there's no missing or damaged driftlimator panels, that the air seals are properly installed, and that there is no accumulations in the air passages of the driftlimators. Fouled driftlimators can act like a plugged air filter on your car. It can actually choke the fan for air. The fan stacks, considerable thought and calculation, modeling, and testing goes into the design and construction of a fan stack. It directly affects the proper flow of air through the tower, provides an eased entrance for the air to the fan, and smooth profile below and above the fan. It houses the fan assembly, preventing the recirculation of air moved by the end of the blades. Stacks 10 foot and taller provides a velocity recovery effect, increasing airflow. The stacks should be inspected for cracks, loose or missing hardware. The hold down hardware, particularly the hurricane bolting blocks, should be examined to make sure that they're in good order. Stack panels, looking for cracked or soft spots and voids, and making sure that the drive shaft guards are intact and have no damage. Mechanical equipment. Fans must operate at their optimum level. The tip clearance between the end of the blade and the fan stack should not exceed 1.5 inches, and that's because there will be a recirculation. The larger that distance is, the more recirculation or lost airflow will occur with the fan. The fan hub seal should be properly installed to prevent recirculation of the air. And this is an item that's particularly important to maintain the efficiency of the cooling tower. The fan blade should be pitched to utilize all the available fan horsepower. So the plant electrician should measure the fan motor amperage to compare that to the nameplate amperage of the motor. You don't want to use every bit of the nameplate because of the changes in air density, but you want it to be slightly below the nameplate amperage. The other equipment, obviously, is the gear reducer, which we would be looking for leaking input or output seals, bearing wear, excessive backlash, leaking oil line, loose hardware, and proper hardware torque. The fan assembly, inconsistent tracking, check blade pitch, deteriorated fan blades, missing seal disc, improper hardware torque, and blocked weep holes in the blades. The drive shaft, check for misalignment, missing hardware, broken flex elements, hardware torque, and missing set screws. And the mechanical supports for cracked or damaged support materials, extreme corrosion, broken welds, or missing hardware. Regular preventative maintenance will increase reliability of the tower, decrease lost operating hours, and extend the life of the equipment, all adding to the profitability of the plant. Following the manufacturer's user manuals and employing checklists and guides to track the condition of the rotating equipment, maintenance personnel will extend their service life, achieve peak performance, and minimize the chance for unplanned equipment breakdowns. The preventative maintenance of the rotating equipment should be thoroughly documented by cell. Discrepancies found, service items, torque values, and indicator readings should be accurately recorded in the PM report each time a PM is completed. The inspection report should be summarized in an easy-to-follow comprehensive report. The report format should act as a checklist describing each component, detailing its current condition, along with any recommendations for repair and/or maintenance attention. All attaching hardware steel components should include a corrosion grading scale with a ranking of good, minor, moderate, or severe corrosion. Any deteriorated structural member should be ranked by deficiency as minor, moderate, or severe. Each component should be assigned a priority level ranging from 1, repair immediately, 2, repair next 1 to 2 years, or 3, no repairs needed. Supporting inspection documents should include an itemized list of structural members identified for replacement, to include their exact location, quantity, description, and priority. Utilizing numbered transverse and longitudinal bent line drawings highlighting the location of each structural member identified for replacement will be valuable to both the owner-operator and the maintenance person that will be doing these replacements. Inspection photos with annotation provides photo documentation for any recommended repairs. I hope this presentation has provided a better understanding of your cooling tower. And routine inspections paired with preventative maintenance and minor repairs will keep your cooling tower at its optimum operating level, maintaining cold water temperature. Thank you very much for your time.
Well, thank you so much, Jim. That was a lot of very valuable information. I do have a few questions coming in, Jim. First of all, somebody would like for you to please explain the wet bulb frequency.
Okay, the wet bulb frequency is basically the number of hours in the summer season that you will meet or exceed the design wet bulb temperature. So if we use, for example, an 80-degree wet bulb at 1%, I don't know the exact number of hours in the summer season. I think it's around 2,900 hours. If we say 1%, 29 hours out of the summer season, you will meet or exceed that 80-degree wet bulb temperature. And it's not going to be continuous. It's going to be different times of the day that it's going to spike up, and you're going to get to that 80 degrees, or you're going to get past that 80 degrees. But typically in the cooling tower industry, the 1% frequency level is pretty much the standard.
When it comes to the cellular fill packs, how do you know when they're plugged?
Well, that's a good question. A lot of times in the inspection process, the inspectors just look at the top layer, and that's not really representative of what's going on. Usually the filing is towards the bottom. So if you suspect that you have any problems with filing, you really should, at random locations, remove the top layers of fill to get to those lower levels to determine if there's any filing. And the most accurate way to determine the extent of the filing, or if you have a filing problem, is to take that pack out and weigh it. You know, there's manufacturer's data on what the weight was of the pack when new, and you compare that to what the weight of the pack at the time of your weighing will tell you whether or not you have a problem. And, you know, a tower that's really filed, it's not uncommon to see a pack weigh 100 pounds that started out at 28 pounds.
And Jim, we have one final question here, and of course, you went through the whole presentation talking about how important inspections are. How often should those cooling tower nozzles be cleaned?
Well, at least once a year. I personally would recommend that you look at it every 6 months. You know, the crossflow towers is pretty easy since they're open basins. You can see whether or not you've got problems with the nozzles. You can see if there's nozzles missing or nozzles plugged. Maybe there's accumulations of mud and debris in the basins. And, you know, when you see that, you know it's time to clean the basins, which is pretty easily performed. The counterflow is not so easy. You really can't see those because they're inside, and it's going to require confined space entry to inspect them. But again, I can't stress the importance of water distribution. So you might try every 6 months. If you see that in 6 months that everything looks good, you can go to every 12 months. Another thing you can do is actually at the bottom of the counterflow towers, look at your water patterns. If you see heavy streams of water, that means that and I'm talking about almost like a fire hose, you've got a missing nozzle, and that's tearing up your fill. If you see dry areas of fill, you got a plug nozzle. So just walking around the base of the tower is going to give you an indication of whether or not you have a problem with your distribution system. And to a lesser degree, this is true with the crossflow tower. If you step back ways from the crossflow tower and you look through, as best you can, the air inlet louvers, you can see the water. And if you see heavy concentrations of water, then you've got probably missing nozzles, or maybe your basin curbs are separating. If you see dry areas of fill, then you've got plug nozzles. And the thing with distribution, if you don't get the fill wet, you're not going to get any heat exchange. And if you have heavy concentrations of water, that forces the air to channel around those heavy concentrations of water, and that's going to reduce the capacity of the tower.
Okay, Jim, thank you very, very much. Folks, this concludes today's webinar, and as a reminder, I want to let you know there will be follow-up information, including the presentation, available for today's participants. Once again, a very special thanks to Jim Smith. He is the president of Star Cooling Towers, LP, and if you would like more information, you can go to starcoolingtowers.com. If you'd like information from Jim, go to sales@starcoolingtowers.com. I hope everyone has a wonderful day, and thanks again for joining us.